Hello, everybody. My name is Mihai Dogariu. I am part of University Politehnica of Bucharest, and today I would like to present to you the work that I've done before and also during my secondment at JR, entitled Object Detection with Ensemble of Classifiers. The presentation is structured in 4 chapters, let's say. I will talk a bit about the context, then the approach, a short discussion about the results, and also some insight about the future work. The first and also quite important part is the context one. So basically, having this subject of few-shot object detection implies several different aspects. So first of all, the part about few-shot learning. In few-shot learning, the problem statement is as follows. We start with, let's say, a classifier or a detector or any kind of system, which we train on a base training data set. This base training data set is quite large, so it's the usual norm for example, let's say ImageNet and stuff like that. So you have a well-defined data set, which is large enough in order to have some good results with your system on it. Then, after that, there is the second step, where you want to introduce new classes. You want to introduce n novel classes. But the tricky part, or let's say the difficult part here in few-shot learning, is that each such class contains only k samples. This number k is usually quite small. It can be 1, 2, 5, 10, or maybe 30, but it's usually less or equal to 30. So now what you want is... sorry?
Acabo de tener que hacer una presentación.
Oh, okay. I think that was a question for us. Okay. Okay. So the case samples that you want to now adjust your system on are very few. That's why we have the few-shot learning scenario. This is called the n-way k-shot learning, let's say, procedure. On our example here, let's say that these are the n novel classes, each such class with a very low number of images. Then, at the last part of the training process, you want to perform classification solely on these novel classes. So after you trained with only, let's say, 5 images for each class, you want to be able to detect that class can be assigned to this query image, for example. We have this parrot or this duck. So the problem is quite complex because you have a very low number of samples, and your previously trained system was used to seeing a great deal of samples, maybe thousands. And now it has to deal only with 5, 10, or 30 new images in order to perform a correct classification. Okay, now moving on to the few-shot object detection. It takes the same few-shot learning goal as in the previous case. So it's just few-shot learning, but applied to object detection. About the object detection, here we have to perform two important tasks. We have to perform classification and also localization of multiple objects in an image. Ideally, we would like to detect each different object in the image, but of course that is very rarely possible unless we have a very strong data set and a very strong model as well. The output of such a system consists of 2 characteristics, let's say. We have the object class, which you can see here as a label, and also the object coordinates expressed as the bounding box surrounding each object individually on the image. Now, the third subsystem, or let's say the third part of this entire approach, the ensemble learning. This ensemble learning is very similar to fusion, to feature fusion, let's say, either late fusion, early fusion, or any other kind of fusion. The only difference is that it is done not on the feature vectors per se, but on the system level, meaning that when we have several similar systems, each performing the same task, we want to run them and then collect their individual outputs, combine them in an intelligent way, and this is basically the ensembling part, and then output a decision. This decision ideally should be better than each individual decision from these n systems. So here we want to take advantage of the fact that one system can perform better than all the others in a very narrow, let's say, scenario. And we want to leverage the advantage from each individual system such that we can create the whole which is better than the individuals. Meaning that the ensembling strategy, also the way that we pick these decisions and how we can, let's say, weigh them and combine them is essential to a good output. Okay, now regarding our approach. We started from the paper proposed by Wang. This paper is very popular in the few-shot object detection field because, as the title says, it's a frustratingly simple few-shot object detection. So it's a very simple approach in which they perform the few-shot object detection, frustratingly simple, as the title says, and it also yields very good results. So I will just make a short introduction of this method. Also, this is the reason why we also cooperated with JR, because their approach was also based on the same paper by Wang. And seeing that both our team and their team works on the same type of model, we decided to combine forces and then have this secondment. So in this scenario, the few-shot object detection goes as follows. In the first stage, we fine-tune. We perform a normal training of the entire system on the base dataset. This base dataset, as I mentioned previously, it's quite large. We have enough instances of each class that we want to detect. And then it goes through such an object detector. This object detector was chosen to be a faster RCNN, for example, but it can be almost any other type of feature, almost any other type of object detector. And it contains several key components. We have the backbone, then the region proposal network together with the region of interest pooling. We can combine, let's say, these two and say that we have a region proposal network on this part. Then we extract features from these regions of interests. And based on those features, we perform a box classification and also a box regression. Okay, so in the first stage, this entire system is trained normally. We train it normally on the base dataset, which contains only 60 classes from MS COCO, which MS COCO consists of 80 classes in total. So we leave 20 classes aside for the next stage. And the system is trained normally as you would train any other object detector. Then in the second stage, in the fine-tuning stage, we freeze the entire part responsible of processing each image up until outputting a fixed feature vector, and we label this entire block as a fixed feature extractor. So this part is frozen. And then the input is switched from the base dataset to the novel classes. In these novel classes, we have a balanced dataset between images from the base dataset, which are only a few, and also from the novel datasets, which are also only a few. This few is, as I mentioned, 1, 2, 3, 5, 10, or 30 images. So we want to perform the new object detection only on these new classes represented by only a few images. We keep the same loss function for the object detector. We keep now a lower learning rate because we want to fine-tune what has been previously trained. And only the box classifier and the box regressor are left to train in this stage, keeping this part frozen. Now, starting from this scenario, we wanted to also introduce the ensembling, meaning that instead of having only one system perform all this pipeline, we put in parallel n such systems, capital N such systems. So here we have a normal object detector where we have the backbone, the region proposal network, the feature extractor, and then the classifier and the regressor. And also the same thing multiplied n times. So we have n systems running in parallel. And then finally, based on the output of each such system, we want to perform this ensembled classification and also regression. But the interesting part about this approach is that during the second stage, the entire part about the backbone, the region proposal network, and the feature extractor is frozen, meaning that if we do this to n different systems, we will end up with probably the same output for each of them. So it's not, let's say, it's not efficient to do this n times because each of them should have, in the end, the same output. Each of these n submodules should end up with the same output towards the classifier and the regressor. So our idea was to drop all these n modules and keep only one of them. So we kept only one common backbone, a region proposal network, and the feature extractor, which is the frozen part during the fine-tuning. And then we performed the ensembling only in the classifier area. So we put n classifiers in parallel. This is very similar to the previous, let's say, setup, with the only difference that the purple area is reduced n times. It's n times less space that we want to occupy, n times less processing time. So we keep only n classifiers running in parallel. These ones are trained with a module dropout of 60%, meaning that each classifier has a 60% chance of being dropped during the fine-tuning phase, and only one regressor. We kept only one regressor because these n classifiers all act on the same proposed region. So we do not need to regress n different bounding boxes. We only want to address one bounding box, but with n different classifying results. And the outputs of these n classifiers are then treated in an ensemble fashion in order to reduce them to only one single decision. So the strategy that we applied in the first place was the non-maximum suppression. This is very common for the object detectors, and it also works very well on our proposed approach because it fits very nicely with this part of having one bounding box with n classifying results and proposed classes. And performing non-maximum suppression on these results leads essentially to what we want in the end. So to have only the best decision for each bounding box as it is seen through the eyes of n different classifiers. So this is the gist of the gist of our approach. It's quite simple, but it also fits very nicely in this context of few-shot object detection. So about the results, we compared the results that we obtained with the ones in the original pipeline of Wang et al. And we have seen a mild improvement. So when evaluating the average precision at 0.5, meaning at the intersection over union between bounding boxes of 50%, we have obtained 10.1% average precision on the 10 shots and 13.6% on the 30 shots. This is compared to 10.0 and 13.4. So we have an improvement of 0.1 for the 10 shots case and 0.2 in the 30 shots case. When we compare our approach to the classical ensembling strategies, because we've dropped all that processing that is done n times, but it's redundant in our case because everything is frozen on that part. We obtained an n times speed up compared to the classical ensembling, and also n times less memory required. These are very important aspects because when we think about what has been added to our system in order to make it simulate an entire ensemble of networks, we see that only in the last layer we have added, instead of one fully connected layer or one convolutional layer, we have now n such layers. When we look at the number of parameters, the surplus, or let's say the added resources that we need are negligible. So basically, it's virtually no added cost whatsoever. This means that compared to n times running the same system in parallel, we obtain a very important speed up and also a very memory efficient setup. Now, talking about the entire framework as we've designed it, this kind of approach can be applied, let's say, to any type of few-shot object detection algorithm, which has in its last layers a classifier. And most of them do have it, and especially the two-stage approaches, such as the RCNN family. It is not dependent on the model, so we can switch it between faster RCNN, mask RCNN, YOLO, and all types of few-shot object detectors. And the very important part for us was that we managed to integrate it with JR's code base. So they were working, as I've said, on the same base, on the same code base, but they have made their modifications in order to advance their research. And we managed to branch from their project and integrate our approach such that we obtained a very homogeneous ecosystem together with their algorithms. Then, having this platform up and running, we also proposed a paper in the demo session at MMM 2024, and it has also been accepted. Now, regarding the future work, in the few-shot object detection, let's say, setup, we want to extend this work to benefit from different ensembling methods. So the most important part is the ensembling strategy, meaning that we want to invest some time here and effort in order to see which strategy works the best for our case. We want to try 3 different ensembling methods, which we've found to be quite successful in a similar paper by Nikita Dvornik. We want to test the independent ensembling, which is very similar to what I have done. Then the diversity ensembling, where we want to introduce some randomization in the model training. This theoretically works very well for numerous models, so in the number of 15, 20, 30 models, and so on. And also cooperation ensembling, where we want to encourage these conditional probabilities, to be as similar as possible, by applying a symmetrized Kullback-Leibler divergence in the loss function. This one works very well for a low number of models, meaning up to 5 models, or let's say 5 to 7 models. And also, we want to test some different weighting strategies in the ensembling stage. So we want to assign different weights to individual classifiers and see which is the best strategy in order to obtain the best results. Okay, that would be all. Thank you for your attention.